Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The reaction shown is a base-catalyzed isomerization of one alpha-beta-unsaturated cyclopentane to another. The key mechanistic question is, what open-chain diketone intermediate could undergo an intramolecular aldol condensation with dehydration to give both the starting material and the product? Step 1. Identify the carbon skeletons. The reactant is 2-ethylene cyclopentane 1-1 and the product is 2-dimethylmethylidine cyclopentane 1-1 isopropylidine cyclopentanone. Both are 5-membered ring enones. Numbering the carbons, the ring has 5 carbons plus the exocyclic alkene substituent. Step 2. Retroaldol analysis. Under base catalysis, an intramolecular aldol condensation of a diketone can form cyclopentanones. Working backward, retroaldol plus hydration of the double bond, the cyclopentanones can be opened to a linear diketone. The retroaldol of 2-ethylene cyclopentane 1-1 and 2-isopropylidine cyclopentane 1-1 should lead to the same diketone intermediate. Step 3. Identify the diketone. For a cyclopentane formed by intramolecular aldol condensation of a 1,6-diketone, heptanidione, the ring closure involves C1 and C5, or equivalent. Heptane 2,5-dione, CH3, co-CH2, CH2, co-CH2, CH3, i.e., 5-methylheptane 2,5-dione is not right. The correct compound is heptane 2,5-dione, CH3C is equal to O, CH2, CH2C is equal to O, CH2CH3, can undergo base-catalyzed intramolecular aldol condensation. The alpha carbon of one ketone attacks the other ketone carbonyl, forming a 5-membered ring. Depending on which alpha carbon is deprotonated, one gets either the ethylidene product or the isopropylidene product. This accounts for the equilibrium between the two cyclopentanones. Step 4. Confirm option C. Option C is drawn as a 1,5-diketone. Heptanidione CH3C is equal to O, CH2CH2C is equal to O, CH2CH3, heptane 2,5-dione. This diketone has two different sets of alpha hydrogens. Base-catalyzed intramolecular aldol of the terminal methyl alpha proton gives the ethylidene cyclopentane, and deprotonation at the other alpha position gives the isopropylidene dimethyl product. Thus option C is the common intermediate for both isomers. Step 5. Eliminate other options. A is a linear enone, not a diketone, so it cannot undergo intramolecular aldol to form the cyclopentanone ring directly. B is also a linear enone, monoketone with alkene, not suitable as an aldol intermediate for ring formation in this context. D is excluded because C correctly fits. Therefore, the correct answer is C. Therefore, the correct answer is option C.